So the heat of reaction is a state function. And that makes it really useful. And so we need to go over some sort of rules here for what to do with these numbers. And then hopefully it'll become clear why we're doing this. So if we look at this reaction, and this is carbon plus oxygen to make carbon dioxide, and here's the heat of reaction, delta H. If I have twice as much carbon and oxygen, I'm going to get twice as much heat, right? Delta H is written for the reaction as written, for these molar amounts. If I write the reaction with 2's in front of everything, essentially doubling the equation, I'm going to get twice as much heat. So I have to double delta H. So if you multiply the reaction by a factor, you have to multiply delta H by the same factor. If I write the reaction in reverse, so this was an exothermic reaction. Carbon plus oxygen making carbon dioxide was releasing energy. If I do the reaction in the other direction, I take the carbon dioxide and I make carbon and oxygen out of it, the heat exchange is going to be the same, but it's going to go in the opposite direction. That make sense? So if I do the reaction one way, it's negative. If I do the reaction the other way, it's positive. It's like a transaction again, right? If I move money from my checking to my savings account, it's negative for my checking account. If I move it from savings to checking, now it's positive, right? So it's the direction is the sign. And here's where the state function of it comes in. If we can express the reaction as a series of steps, whether or not those steps actually occur, then delta H for the overall reaction is the sum of delta H for the individual steps. So we've got an energy diagram here to help us visualize what's going on here. So we have A plus 2B reacting to form 2D. That's what we're interested in. But we're not able to measure that directly. But we can measure A plus 2B going to C. We can maybe look that up, and we know delta H for that reaction. And we know delta H for C going to 2D. So let's look at these individual steps. So I've got A plus 2B is making C. And that's delta H1, some number. And I've got C going, well, let's do it this way. C reacting to form 2D. And that's delta H2. What happens if I add these two chemical equations? We've done that, right? It's just like adding math equations. A plus 2B makes C, and the C turns into 2D. So these C's, the C gets made and it gets used up. So the overall is A plus 2B forming 2D. So what's the heat of reaction then? It's the heat of reaction of the first one plus the second one. So if we can add the reactions, we can add the heats of reaction. Any questions? We can do this because it's a state function. Did this actually occur by making C and then making 2D? We don't care. It's possible for it to do it that way, and the difference is the same. It's a little bit like that elevation problem. So here you are, let's make the mountain. So here's the mountain, and you were on top of the mountain and you're going back down to the bottom and you want to know the elevation change. But instead of going down the mountain, you got in a helicopter and you went up here and then you came down. And from the helicopter you can measure the altitude that you went up and then all the way back down. So this number and that number, this one's a negative number, this one's a positive number, added together give you this. The change in elevation is the same regardless of whether you actually went in the helicopter or not. But somebody went in the helicopter and measured it that way. And so we can say, well, yeah, it's the same. Any questions? Okay. And that's known as Hess's law. I'm not going to quiz you on that name, but we need to refer to it, and so use Hess's law. That's it. If you can add equations to get the thing you need, you add the delta H's. So here we're tasked with finding the heat of reaction for this chemical equation. And we're given some other chemical reactions with known delta H's. So what we want to do is we want to take these equations and combine them so that they add up to make that one. This ends up being kind of like a logic puzzle. And there's not only one way to do it, there's multiple ways, and you kind of go around. It's a little bit like balancing equations. You just have to fuddle your way through. I just made up another word. So I'm looking at this and I'm trying to figure out, well, how am I going to put these together to get that? So maybe I'll start by looking for this N2O as a reactant. So that doesn't, the first one doesn't have it. This has N2O as a reactant. So I'm going to write that down. Where am I going to write it down? I'll write it down here. So 2N2O going to 2N2. Sometimes the states are important in these. And delta H for that. Did I do anything to the equation? Did I multiply it by a number or change the direction of it? No. So delta H is just the same as I was given, 163.2 kilojoules. Okay, so there's my reactant. There's too much of it, but we'll see what happens. The other reactant I want is NO2. So no NO2 there, no NO2. This one has NO2, but it's a product. I can write the reaction backwards and make it a reactant. So I'm going to take this one and reverse it. I'm going to get 2NO2 gas, 2NO plus O2. Because I reversed it, then I changed the sign on delta H. So it was negative, now it's positive. Okay? So I've got reactants here. I'm supposed to get 3 NOs as my product. I've got 2 NOs, but then I've got all this other stuff in here as well. This reaction, not that one, I already used that one. This one in the middle. If I put that one in there, I could use that to get rid of the O2 and the N2. I don't want those in there. So I'm going to write that middle equation here. N2 plus O2 making 2NO gas. And I haven't done anything to that, so I'll just copy its delta H. Okay, so now I'm going to see what happens. I need these to add together to get this. Well, I've got some things that are going to cross out, right? I've got O2 would cancel with this O2, but then I've got another one here. So that's going to be a problem. And I've got 2 N2s, and I've only got 1 N2 over here. So if I multiply this bottom equation by 2, so multiply all the coefficients by 2, and I multiply delta H by 2. Now when I add these together, I've got 2 nitrogens here with the 2 nitrogens there. And I've got 2 oxygens and 2 oxygens, and those cancel out. What's happening is I made 2 nitrogens and I used 2 nitrogens. I made 2 oxygens and I used 2 oxygens. So they're not around anymore. So then let's write down what's left. 2N2O plus 2NO2, making, now I've got 4 and 2, so that's 6. And delta H is the sum of that old mess up there. So I've got negative 163.2 plus 113.1 plus 182.6 times 2. 315.1 kilojoules. Now, this looks a lot like that, but is it exactly the same? No. What's wrong with it? It's multiplied by 2. All the coefficients are 2 times too big, right? So what I need to do to get from here to there is divide by 2. If I'm going to divide all the coefficients by 2, I divide this by 2 as well. So I'm going to divide by 2, so that becomes a 3. This becomes a 1. This becomes a 1. And then I divide this by 2. Calculator says 157.55 kilojoules, and that should be at 1 decimal place. So then up here I'm going to call that 157.6. Any questions? What Hess's law does is it allows us to calculate a heat of reaction for a reaction that we may not be able to monitor, or even might not be able to cause to form or cause to happen. But if we have information about other chemical reactions, we can add these together and still predict what delta H is for that reaction.